All right, let's talk about the inverse normal. So the first thing we need to do is to understand a little bit, go over the empirical rule and percentile. So here I have a standard normal with mean 0 and a standard deviation of 1. With the standard normal, we have the mean here at the middle, and then we have one standard deviation to the right, or things that are above average, one standard deviation, and then two standard deviations. That's why the 2 is there. And then below average, or one standard deviation below, and then two standard deviations below. What does that mean? If you have a point here, let's say, that point is one standard deviation above the mean. So if the mean was 12, let's say, and the standard deviation is 3, you add 3 to 12, that gives you 15. So this point would be at 15. Okay. Percentile. Now, percentile is the cumulative area from left to right, or the area below, right? So if you go from negative infinity all the way up to 2, negative 2, right, which is the same thing as the probability of z less than minus 2, and you can see the inequality is pointing to the left, right? So what does that mean? It means that from negative infinity to shading all the way to negative 2, it's 2.5%. So what? Well, it means that if there's a point here, let's say there was a point right here. Okay, let's say there's a point right there. That point, right? How likely do we choose that point? Well, it's, or that point being below negative 2, how likely is it? It's going to be like 2.5% likely. Is that very likely? No, it's probably unlikely that you'll choose a point at random. Okay, let's keep going. Let's keep going. Let's shade more. Another 13.5%. From here to here is 13.5%. That's part of that empirical rule. Well, not quite. The empirical rule is different, but it's the same concept. Here, if we say what's the probability that z is less than negative 1, well, that means we're going to be shading everything from negative 1 all the way to negative infinity. That is going to be 16%, and that's what the 16%. You see, we have this row of percentile, which is cumulative. You're adding more to it as you move to the right, as you shade more to the right. Here, if we shade half of the standard normal, well then we're going to get 50%. That's what it says, 50%. Remember, this keeps shading all the way to negative infinity. You can see that if the probability is less than, or the probability of z less than 0, then that means we're going to be shading from 0 all the way to the left. And if you keep shading another 34%, then we got 84% altogether. So all this shading piece, all the orange piece that goes all to negative infinity is 84%. Again, what does that mean? It means something like, what's the probability that z is less than 1, right? Any number that's less than 1 is going to be captured in that probability. In this case, it's going to be 84%. How likely is it that you'll find a point here, let's say, based on, the probability of z being less than 1? Pretty likely, it's 84%. 84% is a pretty high number. Let's keep going. And then probability of z being less than 2, that's 97.5%. So anything below anything below 2, right? And this is a z-score of 2. Less than 2, there's a 97.5% chance that you'll choose it at random. Which, again, from here to here is another 13.5%, and you add that to 84, it gives you 97.5. Okay, that's a lot of talking about empirical rule and percentile. This is a very non-traditional way of talking about this. But one more thing, if you keep shading all the way to the right to positive infinity, then the whole thing is 100%. All right, let's talk about how population mean and the population standard deviation is connected to this whole idea of percentile and also the idea of the empirical rule. So here I'm shading the kind of like a template, you might say. So all this orange piece is 100%. Now you'll see that down here I have a random variable of x. You see, z is for the standard scores of 0, 1, 2, all normal distributions. Any normal distribution can be converted to z through this formula. You might have seen it before, right? If you have an x value and you have mu and sigma, you can get z. And then you can determine how far away x is from mu based on sigmas. You'll see that in a minute. So you have mu, which is in the center. So again, x is any problem that you encounter that doesn't have z-scores, right? Like growing bananas, or babies that are dying, the amount of babies that die, or the baby's weight, or the wear on tires, or how long a computer lasts, or the gasoline prices. Most things that you measure, most, not all, but many, have this normal distribution. But these different systems that you study will have a mean and a standard deviation, and this is the mean that we're talking about, and you'll see how that works too. But one standard deviation over, you add one standard deviation. If you're 2 standard deviations over, then you add 2 standard deviations. You see, you add 2. I'm going to show you a practical way of doing this in a minute. You subtract 1 standard deviation to the left, and you subtract 2 standard deviations to the left. You do this for the random variable x. Okay, this is a template so that when you get the word problem, you can fill this in right here. That's the whole point on this. This piece right here is a template that's automatic. Okay, so let's say you have some system, right, that says the mean was 12 and the standard deviation is 3. The 12 goes right here in the center because that's the mean, that's the population mean. Then you add 3 to get 15, and you add another 3, that gives you 18. What does that mean? That if a point is here, which is a point of 18, well, it's 2 standard deviations away, which makes sense. How's that? Well, again, here's a formula. Z is equal to x minus mu over sigma, right? X is 18, because that's the random variable, minus mu. What's mu? Mu is here. This is sigma. I'm sorry, this is mu. This is mu. This is sigma. Mu is 12. Okay, 12. Divided by sigma, which is 3. 18 take away 12 is what? 12, 13, 14, 15, 16, 17, 18. 6 over 3 gives you 2. That 2 is this 2. Z is equal to 2. That means that 18 is 2 standard deviations away. 2 standard deviations away from the mean. There's a lot of things why that's important. And one of the reasons why it's important to calculate it is because we can standardize many of these problems into one type of problem, which helps us solve it. But that's not what this is about. This is about the inverse normal, which we will get. So we subtract 3 from 12, and then we subtract, in this case, 6 from 12, because we have to subtract 2 times sigma, right? Sigma, again, is 3. So 12 minus 3 gives you 9. But again, this right here is something to fill in to make the appropriate values of the spread from the mean for the random variable x. Again, random variable x is what you're studying. Z is always present in these problems. Percentile is also present in these problems as well. So what you can do is you can get rid of this template piece right here and then move that up so it can match. You see that? So values that are 15 have a standard deviation of 1 standard deviation above the mean. Okay, which is right here. Yes, you can have values that are half of a standard deviation, which would be around here somewhere. Half between 12 and 15, right? Which would be 1.5, which would be what? 13.5, right? Okay. So now that we have this idea of the empirical rule, which really I didn't teach you I'm not teaching you it's not teaching, but I'm not talking about the proper empirical rule that you see. Empirical rule you'll see in most YouTube videos is they'll say that from -1 standard deviation to 1 standard deviation, that's 68% of the normal, which is 34 plus 34. And then from -2 standard deviations to 2 standard deviations, when you shade between those two, that's going to give you 95%, or approximately 95%. Sometimes they'll give you a different value. And sometimes they'll do 3 standard deviations. I don't see how 3 standard deviations make a big difference. It's going to be up to 99 point something percent. Okay, and of course if you shade the whole thing, that's 100%. Again, this is all review for our inverse normal. Now let's do a problem. Let's say we have some type of candy factory, and each box, right, should have 24 candies, right? So here we say X represents the number of candies in the box, and the box on average should have 24, and then should have a standard deviation of 3. What does this mean? Well, a couple of things, but before that, let's read the problem. On the 84th percentile, how many candies are expected in a box? So if the box is at the 84th percentile, how many candies are expected in that box? Well, that is going to be straightforward. First of all, let's shade up to the 84th percentile, which is right here. See that? 84th percentile goes from -infinity all the way up to here. This is important about percentile, that you're shading from -infinity to a certain point. In this case, it's going at the first standard deviation, right? 1 standard deviation from the mean. Not all these problems are going to be this easy. The scale, of course, is based on the spread. And of course, problems could be like 17th percentile or 38th percentile. And you don't see 17, nor do you see 38, right? So keep that in mind. Right now, we're just doing something that you can visually see. So what? Well, what you can do is you can do the random variable right here. Remember the random variable? The random variable gives you the opportunity to write down your mean and then your spread. 24 plus 3 is 27, plus another 3 is 30. Why am I adding 3? 3 is the spread, 24 is the mean. The mean is the middle, 24. And then how is it spread out? Right? The variation from the mean. It's spread out by 3. 24 plus 3 is 27, plus another 3 is 30. Okay, and then you can also go down. Subtract 3 from 24 is 21. Subtract 3 from 21 is 18. 18 is 2 standard deviations from the mean. Again, what about 2 standard deviations? What's so special about that? It means that there are less chances that the box will be 18 than compared to a box at random, right? There's more boxes at 24. So again, this is all about chance, right? The chances that you pick a box is more likely going to be 24, 23, 25. More likely, because if you remember, right, in your like histograms, right? When you're doing histograms, right? The taller the bar, the more likely it's going to be in there, right? The more frequent it would be. Same thing with this, right? If there are there many boxes with 18? No, not many. So it's unlikely you're going to choose those type of boxes. I know we're going a little bit farther, or should I say further from the topic. So 27 is at the 84th percentile. See that? Again, on the 84th percentile, how many candies are expected in the box? If we look at our template that we filled out, remember we filled out the random variable x. What is random variable? It's the thing that we're studying. Number of candies in the box. So we can see that 84 is in conjunction with 27. So on the 84th percentile, how many candies are expected in the box? Well, we're expecting 27. Okay. Well, 84th percentile, right, is one more time cumulative. So what about your calculator? How are you going to use your calculator on this? Well, we can use something called the inverse normal. We use the percentile, and it's percentile, and we're going to use the mean and the standard deviation. And it should give us an answer of 26.983, which is close to 27. Now, let's try this app here. Okay, I tried the app, it didn't work. That's all right. If you put in your calculator, so you hit second vars for distribution, and you look for, I think it's the third button, inverse norm, you put in 0.84, 24 and 3, gives you the answer. So you're expecting, on the 84th percentile, you're expecting about 26.983 candies. Let's try another one. Let's say you're looking at the weights of sardines. The top 5% of sardines are after what would be the minimum weight of these sardines, right? The top 5% of these sardines, because I guess they're bigger and have more oils or something. The thing is, what's the minimum weight? They could be very large in weight, but what is the minimum weight that is considered, one of these sought after sardines. Top 5 means that it's going to be shaded from the right. So our random variable, we know the mean, the standard deviation. The mean is 8. The standard deviation is plus 3. So 8 plus 3 is 11. 8, 9, 10, 11. Add another 3 to 11. 11, 12, 13, 14. Right? That's the spread of the data. And then subtract 3 from 8 is 5. Subtract 3 more is 2. So that's 5%. 5%. 5% is kind of close to 2, but not quite. Remember, at 2 onward is 2.5%. So 5% is a little bit more. It's not between 1 and 2, but close to it. And if we shade this piece here and we draw a vertical line, it might hit close to 13. 13 might be the minimum value that is sought out. 13 what? Whatever it is. 13 ounces, 13 pounds. Is it? Well, let's say ounces. That's not pounds, right? 13 ounces is the minimum, right? 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 25. Sure. Is there a sardine that is 25? Could be. You don't know that. But not very likely. Right? But those sardines that are 13 as a minimum weight, yes. That's the answer. But that's an estimate. We're estimating. So how do you figure it out? Well, you got to use the inverse normal again. But the inverse normal on your calculator only likes percentile, okay, which is this empty piece. If you put 5% in the inverse normal, it's going to be wrong, okay? That's not the right answer because it's not going to give you 13. What it's going to do is if it shades over here to 5% somewhere, it's going to give you an answer about 3. And if we do it and you get an answer of 3, you know you did it wrong because you need an answer of 13. So, inverse normal, we got to put a percentile, right? The area below. And that area is going to be 0.95. And then 8 for the mean, 3 for the standard deviation. And look, you get 12.934. What is 12.934? 12.934 is the minimum weight that you need for the sardines. If you have any weight above 12.934 or close to 13, any sardines close to 13 or above, that's sought out. So you have to, people probably pay more money for it. So this is a lot of information for inverse normal. The important thing is that the random variable x, which is the problem that you are studying, is somehow connected to this empirical rule, right? This percentile thing, right? This right here. Percentile and empirical rule are somehow connected to the random variable x. You see, when you do problems, again, like tires, like candies, like gasoline prices, all those they all have different normal distribution. They all have different shapes and sizes of the normal distribution. Okay. Some are taller, some are thinner, some are wider. And the thing is, you can put all those together into one form, which is the standard normal. And because of the standard normal, you can connect that with the percentile. And it really doesn't matter. You don't have to have the standard normal, but if you did have the standard normal, which is this one, then the standard normal matches easily with the percentile and with the empirical rule, meaning from -1 to +1 and 68% and so forth. And, the empirical rule doesn't say anything about taking little pieces, but you can take little pieces, right? If -1 to 1 is 68%, then half of this should be 34. It's not taught that way, but if it was, you could. Anyway, percentile is pretty neat because as you go from left to right, you can figure out the shading piece. And because of that, you can do this inverse normal, right? In this case, 84th percentile, they want to know what X is, right? 84th percentile is right here, which matches to 27. That's the estimate, right? But when we use the inverse normal, we get an exact value of 26.983. And when we did the sardines, it says top 5%. Top 5 is right here. Top 5 is not here. Top 5 is not there. That's the bottom 5, right? Or the 5th percentile, right? Right here is the bottom 5. And again, if you put 5% or 0.05 here, this answer wouldn't be 12. It would be more closer to 3.00, right? Because you're doing the wrong way, or you're going the wrong way. Okay, hopefully that's something that is helpful. And don't forget to look at the other videos on the empirical rule, a little more traditional look and feel, and percentile. You can get a sense of how are these things calculated.